I'm going to start sharing my slides, and as I get going here, just want to remind everyone that we're here representing the San Jose Astronomical Association, or SJAA, if you like. And we do this kind of public outreach online and also in person in the San Jose Bay Area here in California. And we have all kinds of programs that are open to the public, totally free to attend. Our goal is to educate people about astronomy and the related sciences and help people learn the night sky and just enjoy stargazing. If you like what we do and you want more of it, you can become a member at our website, which I posted in the chat, and we'll share that link again later. So without further ado, let's go ahead and get started. So let me know, interrupt me if there's any technical issues, but hopefully you all can see my screen. And today we're going to be talking about galaxies. So let's dive right in. Okay, these are galaxies. Any questions? Okay, just kidding. Um, so you may have heard the term galaxies. You may have seen pictures of galaxies. There are lots of things in the night sky, and galaxies pictures that you might see could look, something like this. These are all images uh, that I've taken of galaxies from various places, all earthbound. And you can see that even in this small sample, there's a bunch of different shapes. You've got this sunflower galaxy that's it looks like a spiral galaxy, but it's like kind of dimpled and has this funny texture thing going on. But it's got the middle bright area we normally see, and it's circular, elliptical. So yeah, that's a galaxy. Then we've got the Whirlpool galaxy, which looks almost like the question mark. It's actually kind of two galaxies that have collided and formed this weird shape. And we'll see a simulation of how that could happen later in the presentation. And then on the right-hand side, we've got the Andromeda Galaxy. That's what Wolf was showing. You now know how to star hop your way to the Andromeda Galaxy, and you can see it. It's big and bright, and it's really gigantic. And then in the middle, we have a field of a whole bunch of galaxies. This is the Markarian's chain, and all this whole. If you maybe you can't see my pointer.
Actually,
Can you see
oh,
my
there we
pointer?
go. For a
Okay.
moment, it seemed like the pointer was offset from the actual content, but just now it looks correct for me. So, okay, sorry, continue then.
Okay.
Yeah, okay.
Thank you. Yeah, I was looking at my presenter view. So this chain here, and these guys, and these guys, and these guys, anything that's not a very round star in this field are actually galaxies, and they're much smaller, perhaps physically smaller, but definitely further away than these other galaxies. Um, and you can kind of see that. Oh yeah, some of them have this elliptical shape, and then some are kind of fuzzy. This one just looks like a line. What's going on there? Uh, all different shapes and sizes in these galaxies. Okay, these are not galaxies, but what's the difference? You can see that, like the other slide, these all have a bunch of stars. Some of these have really bright middles, just like the galaxies. Um, there's some like fuzziness around them, just like the galaxies, but these images are not actually galaxies. There's something else in the night sky. The two on the left-hand side are what we call reflection nebula. They're these big clouds of gas that are illuminated by stars around them, and they glow in these different colors depending on the composition of the gas and the star and the dust and everything that's reflecting the light. The middle image is the Pleiades, which is a common asterism that you may encounter, but it also has some nebulosity around it, just some fuzzy stuff. This is an open cluster. It has stars, but it's not a galaxy. So we'll get into a little bit more about what characterizes a galaxy more specifically as we go. And then on the right-hand side, this image of M7, again, there's some really bright foreground stars here. They're all clustered together, another open cluster, but again, not a galaxy. So we're going to decode this a little bit in our as we go forward. So I kind of spoiled this slide already, but what's the deal? Some things are galaxies, some are not. Both of these things have lots of stars, cloudy patches, even some dark lanes you can see in the galaxy above. There's like it's bright, and then there's like this kind of black line going through it. And there's bright and dark spots in the nebula, but they are very different. And sometimes it's hard to tell these things apart. So let's follow in the footsteps of early astronomers and try to figure out how we can distinguish galaxies from all the other stuff that we see in the night sky. So let's begin, go way back to a time when we didn't have any telescopes, we didn't have binoculars. All we had were our two eyes and really dark skies because this predates electric lights and all this light pollution stuff that we deal with now. So if you looked up in the night sky at this time, but pre-telescopes, you might see something like this image on the right. This image I took from Yosemite during our this summer. We hosted two-star parties at Yosemite in conjunction with the park, and it was really fun because this is one of the few dark sky places, dark sky sites that are accessible to us here in California. And so the night sky is really dark. It looks pretty much like this with your eyes, maybe not slightly less bright, but it looks really impressive. And so you're someone in prehistory before telescopes, you're looking it up and you're like, wow, there are a lot of stars up there, right? And it's true. There's a lot of points of lights and you can connect them and draw asterisms and constellations like Wolf was going over in the Stellarium demo. And it's great. You can make up stories about that. And this is what you see when you look up. If you look closely, you can see kind of these alternating knots of light in dark areas. This is actually the Milky Way. And we named this feature such because it looked kind of like, I guess they just didn't have coffee and milk, but if you put your milk in your coffee and you kind of make this streak and it's just kind of cloudy, like a glass of milk. So Milky Way, why not? And we also see some smudges. Yeah, I see a smudge here in the middle. That's actually Andromeda again. But if you look closely in a really dark sky site, even with your naked eye, you can see some other smudges, some other faint things that are clearly not stars. Okay, so let's move forward in history a little bit and let's break out the telescope. So Galileo, one of the first people to use a telescope to look at the sky. Galileo looks up at the sky and what does he see? Well, he sees a lot of stars. Well, okay, we know about stars. Um, and the moon is up there. Of course, the moon is something that wasn't in the previous picture, but of course, if you looked up at certain times, you would see the moon as well. And we know that's a different thing, like, clearly not a star. It goes through these different phases. On the right-hand side here, we have actually a sketch from Galileo of the moon going through different phases as observed through a telescope. And you can see this is I don't know what the deal is. Maybe he obviously can draw really well, and obviously doesn't always draw really well either, if you look at his Saturn picture. So here he decided to do a really nice drawing, I guess, and you can sort of see the craters, shadows, and if you look through a telescope, and this last one, what he marked number three, I guess, it really impresses me. I mean, this looks like a great telescopic view of the moon. Um, and it's rendered so nicely in this drawing. So he's seeing new detail in the moon and identifying, you know, thinking about what that detail could actually be, what this moon thing could actually be. And then he also looked at the planets. Like before telescopes, we knew there were planets because we'd see these star-like things that kind of wandered around the night sky. And so they became named planets. And those, we know they're special. So, hey, let's look at those. Galileo looks at Jupiter and Saturn and sort of famously observes these moons or these little points of light that seem to revolve around Jupiter. And those 4 points become known as the Galilean moons. And you can see how he, on the bottom right sketch, how he plots the position of these moons um, over time as he's observing them at different times. He's seeing those dots are switching positions, and that's a sign that something is going on because stars, all the other points of light in the night sky pretty much stay in the same relative position, but these are swapping places left and right, so something's going on there. Uh, so more and more evidence is piling up that okay, it's not just stars out there. We've got the moon, we've got these planets. The planets seem to have their own moons revolving around them. That probably means our moon revolves around us. Things are getting really interesting. So other people look through telescopes. Galileo was in the 1600s, and here we have our friend Charles Messier in the 1700s looking through his telescope and observing the night sky. Um, Charles Messier is about 40 years old, I think, in this image in 1770, which is around the time of the American Revolution, just to give you a little historical marker. And he's looking up at the night sky and he's interested in comets because comets are another thing that we can sometimes see with our naked eye. And great comets are big and bright and dramatic and mysterious. And people often thought they heralded some sort of bad omen that something bad was going to happen when these comets showed up, or maybe something good. They didn't understand it, so they described some special meaning to it. So Messier is like, okay, I want to see these comets. Comets are cool. And he's looking around at the night sky and he's like, oh, this thing, it looks kind of fuzzy. It could be a comet. And oh, no, that's not a comet. Forget it. I don't want to waste my time with this thing again. So he writes it down on the list. He does that for 100, 110 odd objects. And these end up being some of the most well-studied and classic observation targets when we go out to look up at the night sky. Things that Charles Messier was just trying to ignore because he was obsessed with comets, become his trash becomes our treasure. And these things, if you look at them, some of them actually are galaxies, but some are not. Some are just these clouds, fuzzy clouds of things. And if you look at um, one of his sketches. So Wolf showed us the Orion Nebula, the jewel of the winter sky that's coming up earlier and earlier. On the top right corner is Charles Messier's sketch of the Orion Nebula, and this is through a small telescope. We're still talking about like I don't know, maybe 2 inches refractor or smaller, just a small telescope compared to today's telescopes, and he's seeing all this bright nebulosity and a really clear shape, and that's how he renders it. On the background of this slide is a photographic image of the Orion Nebula. And yeah, you can tell that yeah, maybe there's some similarities, but it is this big, bright thing of an interesting shape. There's all these kind of cloudy things around. There are bright spots, different colors. Um, so again, we're looking up at the night sky in this history lesson and we're seeing all this stuff and it all looks fuzzy. And so we call them nebula or nebulas or nebulae for plural. And the nebula basically just means cloudy or fuzzy. And that's kind of how they look through the telescope. So all these things Messier is cataloging, nebula, 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 even if it's, galaxy, even if it's um, an actual, what we now call a nebula. Uh, I guess the star clusters, sometimes the open clusters are more clearly just groups of stars, but even some of the globular clusters, they're so densely packed, they can look kind of nebulous too. So we're calling most things that we're seeing in the night sky at this point nebula. Okay, so now we have entered into the 1900s. We have the capacity to build really large telescopes, and we can see a whole lot more detail. Um, and we can see, okay, these things clearly have different structures. And Edwin Hubble figures out that, hey, these things, some of these things that we now call galaxies, are really far away, much further than anything else we're looking at. Something's going on here. It's got to be something different. But wait, how do we know how far away anything is in the night sky? We're looking at the telescopes, and okay, fine, you can see more detail as you get a bigger telescope. You can see further out in the galaxy, further back in time, as we like to say. Um, but what does that mean about distance, right? It's all a matter of perspective. Like I can see a really tiny car um, far away, and it could be a giant semi truck, but it's just far away. Or, I could be looking at a really tiny car and it's a toy car and it's right in front of me. What does it mean? How can we trust this guy? He says something is really far away. So we need some tools to help us figure out how far things are in the universe. And journey will take us back to proving that the thing that we're looking at, these galaxies, let's say Andromeda, are different, whole different objects, different from the nebula, different from the stars, different from the planets, and way, way further out and worthy of a different designation. So we can't physically go everywhere in space, unfortunately. We can't walk from the Milky Way and follow a path over to the next galaxy, whatever that is. Um, we can't physically travel there because they're too far away, and yeah, can't really breathe in space. There's a whole lot of problems with going into space. So what do we do? Well, some really clever folks have devised different ways of figuring out distances. And over the course of history, astronomers have been able to put these things together to sort of incrementally determine the distance of further and further away objects. And we call this whole song and dance the cosmic distance ladder. And there are arguably many rungs on this ladder. But as this cartoon illustrates, the ones that kind of make up the base of the ladder here that we'll talk about today that help us prove that galaxies are far away are these ones: radar, parallax, Cepheids. This is misspelled, but that's ChatGPT can't spell very well, so I apologize for that. Type 1a supernovae, and then redshift. And we'll talk about some of these things um, enough to help us figure out that galaxies are far away. So we can use some techniques, some math, and to figure out the distance to things in the night sky. Let's climb the cosmic distance ladder. So first one is radar. Maybe you've heard this term used sometime in your travels. If you're watching a movie and someone's on a warship or on a plane, they may have a radar. It might be green with a little dial like sort of sweeping around and little lights pinging on it. Um, that is one way to visualize radar. But what is it specifically? So radar is actually sort of an acronym. It's not a proper, there's an extra A thrown in there just to make it sound good. So radio detection and ranging. This is what radar stands for. What does that mean? This is a method where we transmit a radio wave towards an object, and then the radio wave bounces off the object, and we receive it. And based on that interaction and how long that takes, we can determine what the distance to that object is. So, since light has a fixed speed, the speed limit of light, it's called the speed of light, through any given medium, we know, and we have figured out, scientists have figured out what that speed is. You can measure it in various different ways. You know that speed, and you know that radio waves travel at the speed of light. Then, if you time how long it takes for you to send out a signal and receive it back, then you've got speed, you've got time, and you can compute distance. So if you remember some of your physics from high school, velocity equals distance over time, or if you wanted to solve for distance, you multiply velocity times time. And so using radar, we can detect how far away things are. But there are limitations to this. We can build the neat thing about radar. So you can use any sort of electromagnetic wave. Maybe you're familiar with the spectrum. Radio waves are one, light waves are another, microwaves, um, infrared light. All these things could be used, but radio waves have a nice characteristic that it's relatively inexpensive for us to build very large transmitters and very large receivers. And so we can build these very large dishes to receive things and transmit their radio waves. And the largest things that we can build let us use radar on some of the objects in our solar system, within our solar system. And so we can get the distance to the moon, for example, by pinging radar waves off the moon and receiving them, just like this cartoon. That we can't build a transmitter or receiver as large as the cartoon, just to be clear. This would be like several times larger, or about the size of an entire continent. But it's just a cartoon to illustrate that the radio wave is going out to the moon, and then ping, it comes back, and we receive it.
But you know
And,
what? She's really nice and
very nice.
and accommodating. Yeah. So
um, can we mute Maria,
uh,
please?
I think the
Let's
next
do
time.
this. Okay, got that. So yeah, ping, radar, get distance. That's great. Works for the moon, works for some solar system objects, but it breaks down because we can't build a detector big enough to like ping something off of a star. And radio waves might not bounce off of the stars anyways. You could do the same thing with light, like I said. That's actually called LiDAR. And so you light detection and ranging, LiDAR. And your phone, if you have a fancy enough phone, actually has this in the front of it to unlock your phone by detecting the features on your face. So there's all, and if you, well, you have a self-driving car or have heard of self-driving cars, some self-driving cars have these LiDAR sensors as well to detect their distance from other cars and help it maintain a safe distance from things because you don't want the car to collide with anything, generally speaking. So lots of uses for this technology. The radar version we use to determine distance. Okay, so how do we determine the distance of something that's further away? Turns out we can do it with our thumbs, sort of. So if you're sitting at home watching this or wherever you are, maybe you can do this exercise with me. Try sticking out your thumb and close one eye. Let's say close your left eye and put your thumb over some object that's, a few feet away from you or more. So you have a frame of reference. So your thumb is sort of covering up an object. You've got one eye open. Okay, hold your hand very still and now switch eyes. Close the eye you had open and open the eye you had closed. Where's your thumb in relation to that object you were covering up? If you notice, it looks like something moved. It looks like either your thumb moved or the object moved, depending on which eye you're looking through. And that's illustrated by this image here. That effect
I
is
don't know
called
her. I've never
parallax.
met her.
She's not much younger.
Okay, okay. Can you guys hear me?
Yeah,
Okay.
sorry. I was also trying to mute her, and then my list
And
shifted,
then
and I
you
muted you
muted
instead.
me.
I'm sorry.
Okay, no
Please continue.
worries. Okay, Maria, check your mute button. We've heard you a couple times. So, yeah, parallax is what this is called. You can do the thumb experiment yourself, and you can see that effect. So now it turns out that we can observe this effect. Well, maybe not me, but keen-eyed observers can observe this effect in some stars in the night sky. We look at stars, and you saw Wolf in the Stellarium demo change the time, and they all kind of shifted together to a different position. And generally, that's what we see when we look up in the stars. But actually, stars that are closer to us move at a slightly different rate than the stars that are behind us, or rather, they appear to move than stars that are much further away because of that same effect, right? If with you recall with our thumb experiment, if we're looking from one perspective versus another, the things that are closer to us seem to change position, and things that are really far away, and they stay relatively in the same position. So stars exhibit this behavior too. It turns out if let's say you view one of the closest stars to us, like Alpha Centauri or Proxima Centauri, one of these things, um, in this diagram here kind of tries to illustrate this effect. Let's say it's summer solstice in June sometime, and you're looking up at the night sky and you're like, wow, that Alpha Centauri is great. It's right there. It's right next to these other three stars on the left and these other four stars on the bottom. I can find that. And then 6 months later in the wintertime, the winter solstice, you look at the same star and you see, huh, Alpha Centauri is pretty much in the same place, but relative to those background stars, it actually kind of moved a little bit. Those stars that were on the left are now on the right. What's going on? That's an example of the parallax effect as observed with a star that's closer to us than the stars around it. So it turns out that we can actually measure that difference as an angle, and then using that and some clever geometry, we can figure out the distance to that star. And so the way that this is generally done, if you look at this diagram, so you need to be able to observe the stars, apparent motion against those background stars. And so to do that, you need a different perspective, two extreme perspectives of looking at the star. With our thumb, with our left eye and right eye, that was enough to see it for things that were close. But these stars are really far away. So we need a much bigger distance in order to observe that effect than just the distance between our eyes. So the biggest distance we can get, without building spaceships is the Earth's orbit around the sun, right? The Earth, it orbits around the sun once a year. And so if you do one observation now and then another one 6 months later, have the most extreme difference in perspective that you can get as a person on Earth. So do that. And we know that distance, that's twice the distance to the sun, right? Because here you are on the left-hand side, you're one distance away, and then you go to the other side, you're one distance from the sun there. So 1 + 1 = 2. That's pretty well-known concept. And so then if you draw out this sort of geometric diagram, you've got the distance to the sun, 1 AU. You've got the distance to the star, that's the thing you want to solve for. And then you can measure this angle based on your observations. You observe the difference here as an angle. And then that angle, half of that angle, right? Because you're on one side versus the other side, half of that angle here is the parallax. And if you remember some geometry, you can actually use that information to determine the distance from the sun, basically us, to that star. So, you know, if you're not a fan of math, don't worry about it. I'll go through a little bit of math. You don't have to remember anything. It will not be on the test. But I think it's kind of fun because with a little bit of simple geometry, you can calculate the distance to the stars. And so I just wanted to demonstrate how you might go about that. Okay, so we have our diagram and we have our triangle here. It's a right triangle by construction here. So, the distance, this angle here is 90 degrees. And so because of that, we can use some geometry theorems. Maybe you've heard the term SOHCAHTOA in your geometry classes. If not, that's okay. It's just a way of describing how you compute the sines and cosines and tangents of angles in a right triangle like this. So we can use this information along with another fun theorem that says, in this diagram here, this angle theta on the top is the same as the angle below when these two lines intersect. Two straight lines intersect, then those opposite kind of angles are the same. So that's how we calculated that distance. So that parallax angle is known. We observed it. And then we have the distance, 1 AU, and we want to calculate the distance here. And so we can use our geometry theorems and say, hey, the value of the distance, the tangent of this angle tangent is opposite over adjacent. That's what this is. So sine would be the opposite side over the hypotenuse. Cosine is the adjacent side over the hypotenuse, and tangent is the opposite side over the adjacent side. We want to solve for this adjacent side, the D. So we can use a tangent, the definition of a tangent, and we know that the tangent of this angle is 1 AU divided by the distance. And now, now we can solve for that. Oh, I'm sorry. So now we can solve for that. If we measure that angle to be something really, really small, like 0.0001 degrees, then you can plug in that number, put it into your calculator, and you can find that the distance to that star in this example is almost 1,600 astronomical units, 1,600 lengths to the sun away from us. And that's a really cool thing. There's some math, there's some geometry, and there's some really fine measurement involved. but without leaving Earth, we can calculate the distance to some stars. Um, I think that's pretty amazing. And it's worth noting too that this number 0.0001 degree is really small. We can kind of measure that in the night sky. Um, but even still, I just chose that number to have a number. But that small angle still yields a star that's 160 times closer than the actual closest star to us. And so as you might imagine, these angles are very, very, very small. So it requires some precise instrumentation to measure. And the further and further away the star gets, the tinier and tinier that angle gets that we can't, we just can't measure something that small. So this works for stars that are close enough to us that we can measure that parallax effect. Um, and that's great, but it doesn't work for all stars. Okay, forget the math for a second. We know we have radar that can get us within our solar system. We have parallax that can get us a distance to stars that are close enough to us that we can measure that parallax. Um, but how can we get further? So here's step three of the ladder, what we call Cepheid variables. So these are stars whose brightness actually varies over time in a really regular pattern. Um, and the brightness, the amount that it varies, the amplitude is also really regular. So these are super reliable little repeating objects that we can use and have some interesting properties. So Henrietta Swan Leavitt, pictured here on the right hand side of the left hand side picture, um, was an astronomer who studied thousands of stars like this that were all in the relative same region of the sky, actually in the Large Magellanic Cloud, which is, if anyone's ever been to the southern hemisphere and looked up, is one of the bright jewels of the southern hemisphere sky. So all these stars pretty much in the same place, exhibiting these characteristics. And she was able to measure the characteristics of those stars, how much they brightened and dimmed, and how frequently they went through that cycle, what the frequency or period of that cycle was. And because she had the tool of parallax, and those stars were close to enough to us to for us to compute the parallax and therefore their distance, she was able to have the distance to these interesting stars, and she measured the rates at which they change brightness, and she measured how much the brightness changed, and she was able to take those observations and deduce and notice a pattern. And what she found was that, well, actually, the relationship of the stars dimming and brightening, that pattern, dimming and brightening, the relationship of that pattern to its distance was a fixed quantity. And so she could derive this property that, depending on how, if I know two out of three of these variables, I can figure out the third. And so two of those variables being something you can observe in the star, how much it brightens and at what rate, um, then you can figure out the distance to that star. And that's really cool because that doesn't depend on the star being close to us. It can be really far away. It could be close. Because she was able to observe and verify this pattern with the close stars whose distances were known, we're able to apply that to the stars that exhibit this pattern but are really far away. So now we know, in theory, how to find the distance to certain stars that are close to us and certain stars that are far away from us. Okay, now we have the tools to take a step back to where we were with our big telescopes. Edwin Hubble is observing the Andromeda Galaxy. We've seen that a couple times already tonight. And with this really big telescopes, you can actually see some of the individual stars in and around Andromeda. And one of those stars happens to be one of these Cepheid variables. So building on Henrietta Swan Leavitt's work, uses that Cepheid variable, observes it, measures the period of the brightening and dimming and the how much it brightens and dims. And then with those two variables, he's able to calculate the third variable, the distance. And he says, wait a minute, this star in this galaxy is so much further away than anything else that we're measuring uh, in these other nebulae, in these other stars. Um, what is going on? It must be something totally different. It can't be part of the same structure that houses all these other stars that we're seeing in the night sky because it is just so stinking far away. And so this observation, this discovery is a confirmation of theory of what was a theory at the time, a hypothesis at the time that, maybe there are other such galaxies. Maybe our Milky Way is one of many galaxies out in the universe. And so, OMG, so far. I'm sure that's what he would have said if he were here today. Okay, let's take a breather. So we just plotted through the history. We followed in the footsteps of these great astronomers and deduced using the cosmic distance ladder that some things we're looking at in the night sky are just so much further away than others. They have to be their own thing, and we're going to call those galaxies. So how about some pictures? So here's a nice galaxy taken from the Hubble Space Telescope. You can see it's got some familiar structures, these little arms that go spiraling around. Here's a couple more nice galaxies. This one has really nice spiral arms. You can kind of really see that distinctive pattern. This one's pretty cool. It's almost got this other, I don't know if that's another galaxy interacting with it, but it's got this other sort of like funky little smudge going on. Um, these are all Hubble Space Telescope pictures. So Edwin Hubble discovered the fact, among other things, that we're not the only galaxy. There are many galaxies. And his work, gave him enough credibility to have his name slapped on one of the most iconic space telescopes of our generation that takes these beautiful pictures of, among other things, appropriately, galaxies. This is the Hubble Ultra Deep Field image. And you remember at the top of the presentation, we were looking at different examples of galaxies, and some of them were these small kind of smudges. Um, this is a region of the night sky that was otherwise empty. We hadn't really observed anything interesting in it. That scientists and astronomers decided, hey, you know what? What happens if we just point Hubble here and take a really long exposure? And this happens. You see that where there appears to otherwise be nothing, there's actually thousands of little galaxies all strewn about. This was a really neat picture because in addition to having all these cool shapes, like what is this? This is like a plus sign or an X, and then the spirals and smudges. There are just so many galaxies out there. So many galaxies. What's the deal with these galaxies? How do they form? And why are they even out there in the first place? Well, this is an active area of research, but there's been a lot of study on this topic, and I'll present to you summary of kind of what we know so far. So, the Big Bang, you may have heard of it, is widely accepted as the sort of starting the catalyst that creates the universe. And it's massive amounts of energy, really hot, really dense, and it's just this kind of chaos for a while. And then light emerges, elements emerge, things start to cool off a little bit relatively, and expand into the universe we know today. But that expansion happens that in a somewhat non-uniform way, as in if everything was perfectly smooth, perfectly uniform, you'd have like a bucket of water, it's perfectly uniform, and you pour it into a glass, all that water stays together, it doesn't really go anywhere. But you drop some vinegar or some alcohol in it, and then you've got something else floating around, or you've put it in the freezer and it kind of clumps together. Something, not really sure what, causes matter to clump together just a little bit at first, and then more and more over time as gravity takes hold. You start with a little, just a couple atoms together, and then those atoms attract a couple more atoms through gravity, and then so on and so forth. And all of a sudden, you've got these clumps of matter forming stars, and then the stars clumping together, forming these galaxies, and then the galaxies clumping together to form bigger galaxies. And all these interesting formations start to take hold, all because of gravity, all because these tiny little fluctuations, tiny little um, clusters of matter from the early Big Bang that bring things together. So this material is, due to the force of gravity, constantly shifting and changing. So we have a video that is a simulation. This video is only 46 seconds long, but it covers 13.7 billion years. It's a simulation run by a supercomputer and developed by scientists to show how galaxies may form according to our best understanding of the physics of the whole thing. So you can kind of see here the there are some galaxies floating around. The tiniest yellow specks are stars, and you can see gravitational forces interacting, pulling these galaxies together. They start to merge and kind of do this dance. They start to swirl around, they start to spin. You can kind of start to see some familiar structures like spiral arms here thrown out. You can see, there you go, really chaotic spin, lots of dramatic spiral arms, big solid center. You can kind of see other galaxies with similar structures flying around. And this is what we think happens due to gravity over the course of many billions of years, stars and galaxies merging and oh boy, merging and creating more structures. Sorry for that. So as you can see, as galaxies form, they take on all these different shapes and sizes and characteristics. And it turns out that there are some really common ones. And so we can classify the galaxies based on their apparent shape. The three classifications are elliptical, spiral, and other, or irregular. Um, and so I guess they ran out of creativity steam on this last one and just said, if it's not elliptical, it's not spiral, it's irregular. But you can kind of see the distinguishing features of each one. And the elliptical galaxy, it's kind of more diffuse. It's sort of more fuzzy. This would be easily mistaken for a nebula because it's just kind of cloudy. But it has a distinct elliptical shape, or a circle kind of stretched out. So these tend to have fewer features. They just look to us through our observations as these sort of elliptical smudges. So elliptical galaxy, pretty straightforward. Spiral galaxies are characterized by these long, often dramatic arms, kind of like if you had taken like a like a crab's shell or something. It has those kind of spirals. This is what maybe the classic image of a galaxy is this kind of big, impressive thing with these swirly arms and bright knots and dark lanes. So, not surprising, the thing that looks like a spiral, let's call it a spiral galaxy. And then there's kind of everything else. It's not quite elliptical, it's definitely not spiral, but what kind of shape is this thing? It's almost like a horseshoe, or like actually kind of looks like the Star Trek symbol. Um, so it's irregular. Something else is going on here, and it's maybe in one of those weird, chaotic formations that we saw in the simulation. Maybe we're seeing it at it's a point in time where it's going through some changes. Galaxies can also merge. And so here are two images of galaxies that are merging and the kind of shapes that they can create. So on the left-hand side is this cute little guy called the Mice Galaxy. I guess it looks kind of like two mice sort of running around out there in space. But these are two separate galaxies, and they're close enough together that their gravity is pulling on each other's stars and sort of changing. It's velocity, its direction of motion. Just like in that simulation we saw where things are just kind of swirling around. And this is that process happens over billions of years. So when we look at it, it looks like it's frozen in time, but it's kind of in the middle of that process. Likewise, this is M51, the Whirlpool galaxy that we saw at the top of the presentation. And the center here, the spiral arm is pretty clearly a galaxy, but then like, oh, it's got a little punctuation here at the bottom. And this is another galaxy that is interacting with that main galaxy and starting to pull in some of its material into itself, or vice versa. Um, so galaxies merge, and we sort of saw over a large scale, how galaxies come and go and stars come and go into those galaxies. But I have another video that shows how galaxy mergers, might play out and how they affect each other. And you can kind of see the shape of the whirlpool there taking form. This one, I don't think it's intended to be a simulation of M51, but it goes through that phase. And then you can see now, okay, now it looks different. Now there's sort of two galaxies again, and they've both changed uh, permanently. So you can kind of see, oh, we're two galaxies doing our own thing, and then the gravitational forces, they start to interact, and then it gets pretty messy as they get closer. It's stars are flying off left and right. You get kind of that question mark shape, and then all right, and off you go into your own direction again. So galaxies can merge and create all these interesting shapes in addition to those classifications. And so it turns out um, these classifications, you saw how many galaxies there are, right? In the Hubble Ultra Deep Field, so many galaxies in an otherwise empty part of space. So there are so many of these galaxies, and we want to learn more about them. So classifying those galaxies is actually a really valuable thing, and it's something that anyone can do just from their chair or from their smartphone. So if you are feeling empowered with your new knowledge of galaxies and their types, you can actually contribute to science in a meaningful way through this project called Galaxy Zoo. Galaxy Zoo is an effort to, uh, it's an application where anyone can sign on and they teach you how to classify galaxies. You've got a leg up because we've sort of gone through the basics already. And then they give you images of galaxies and ask you to classify. Is this elliptical, a spiral, irregular? Does it have a certain feature? And you look at it, you make your decision, hit submit, and then go to the next image. And there are thousands and thousands of these. And so, if you're ever bored, instead of playing Candy Crush or whatever on your phone, yeah, maybe you could fire this up and do some real science. And these classifications are used. They collect many of those classifications for each object, and so that they can kind of average out what we think it is. And then they use that to train AI models so that the AI models can do classification better. So you're classifying galaxies, and then you're helping to train the software that can automatically classify galaxies so that real meaningful science can be done on these super large data sets where there's just tons and tons of galaxies to sift through. So if you're interested in that, you can go to zooniverse.org. They have not only Galaxy Zoo, but they have a ton of other similar projects. You can listen for bird sounds in the Amazon. You can identify other terrestrial objects that people need help classifying. Lots of cool projects there that you can contribute to and contribute back to the scientific community, all without a PhD.
Yeah, and every
Okay,
now and then actually somebody gets their name on a scientific paper. So just one comment to this, right? So I've more than one occasion I've seen that some citizen science person, ended up with their name on some research paper. So that's cool. So sorry, Carl.
yeah.
Go ahead. Yeah. So,
No,
yeah.
that's a great point. I find it really inspiring too. I mean, maybe it's not everyone's life goal to end up on a research paper, but contributing to science in general is a really cool thing. You chose a career as an artist or a teacher or an engineer or something that's not doing astronomy, but you can still contribute to that. And there are other citizen science projects as well. This is a super accessible one. Okay, so We talked about galaxies, and on a related topic, could go on for a long time, but I just wanted to throw out there are black holes because we've scientific community has discovered that most big galaxies, most large galaxies are believed to have a supermassive black hole at their center. Not just any black hole, but a supermassive black hole. These can be millions or even billions of times the mass of our own sun. So something really, really massive that sits in the middle of these large galaxies and is evidenced by the fact that there's just this extreme gravitational activity in the middle of the galaxy. In order to hold this big galaxy together, there has to be a really, really strong gravitational force at the center. And the only thing that fits that bill in our modern scientific models are these supermassive black holes. And it turns out that our scientific community has actually been able to take an image of a black hole using an Earth-sized radio telescope, which is a topic for another day. But if you can imagine, radio telescopes have this property where you can have one telescope, say over here in one location, and then a mile away you can have another telescope, and you can combine their observations and synchronize their observations such that it acts like you had a telescope that is a mile in diameter. And that interferometry is what that's called. That concept was applied to telescopes all over the world in order to get a high enough resolution image um, of the center of of a nearby galaxy. And this is what they came up with. It looks not quite like the sci-fi movies, but it's pretty cool. There's a dark spot and there's a bunch of bright stuff swirling around it. Further evidence that these supermassive black holes exist and hold these galaxies together. But it's worth noting that black holes are not just for galaxies. You can have black holes elsewhere throughout the universe, and in fact, there are many of these. And smaller black holes can exist virtually anywhere, actually. So that's a little bit of a teaser. Galaxies and black holes share that relationship. What else about galaxies? Galaxies are huge. They have these supermassive black holes. They got billions or trillions of stars in them, so they must be the biggest thing out there, right? Well, not quite. Turns out that galaxies themselves actually cluster into groups. And then those clusters into groups. And the largest structures are these filaments, which is the image over here. You can kind of, I don't know if it shows up on the Zoom call, but there are these kind of lighter dark blue areas against the black background. And you can kind of see the yellow, which are galaxies. They kind of follow these filaments or these strings or these little lines throughout the image. And this is the observed and extrapolated structure of our universe, where all these galaxies, they kind of clump together, and those clumps even clump together in these long filaments. And so we have galaxy groups. Milky Way is part of one called the local group, which also contains Andromeda. And then that's part of these clusters and superclusters. So we're part of the Virgo cluster and on and on. So all that is an effect of gravity. Galaxies collecting stars together, gravity, galaxies, clusters of galaxies together, gravity, these filaments, it's all gravity. Here's a visualization of our portion of the local group galaxies. So if we're here kind of in the Milky Way, you can see there's a ton of these other smaller galaxies here. And then, like Wolf said, the next like major large galaxy next to us is Andromeda out over here. It's a bunch of little satellite galaxies. There's M33, and you can kind of see this distance scale is like 2 million light years away. Um, all of these are part of our local group of galaxies. So if you're ever feeling lonely, just remember that you got a bunch of galaxies in your local group. And just a reminder, you are here. So that's great. We learned so much about galaxies. We must perfectly understand exactly what's going on with galaxies. Well, not quite again. So even though cosmologists, these are the people who study galaxies, have discovered so much about galaxies and their behaviors, there are still some big unanswered questions. And these are hot research topics that maybe someday you will help answer through citizen science or through professional science or just with a really creative idea. So let's talk about one or two of them. One of those is that essentially, so we looked at the simulation of galaxies forming, and it was a 13.7 billion year, dance that these things were going through. So based on that understanding of that physics and the early universe, so we know scientists think that, basically it takes a couple billion years to form these really big galactic structures. But unfortunately, we actually observed that we see some of these big galactic structures um, at a time when the universe was so young that they hadn't had those billions of years to form yet. And so, what's going on there? Well, the community doesn't really know. And the James Webb Space Telescope actually found the farthest galaxy, the such galaxy that kind of flies in the face of this understanding. Um, and it's worth noting, sometimes you may have heard us say this. When we look out into the night sky and we're looking at something that's really far away, we're actually looking at that object as it was some time ago, because light itself takes time to travel. We talked about that earlier. It's like 300,000 kilometers per second, really fast in the vacuum of space, but still limited, not infinite. And stuff in space is really far away. So, that light takes time to reach us. So when we're seeing the light from something that's millions or billions of light years away, then we're seeing, that many years back into the past. And so bigger and bigger telescopes can see further away objects, can see objects as they were farther back in time. And so the James Webb Space Telescope is seeing these objects as far back in time as just 300 million years after the Big Bang. Sounds like a lot, but it's not. Universe is like 16 billion years old. And again, remember, physical models say that, well, it should probably take a billion or 2 years to form a big galaxy like that. But yet we see this galaxy and it is so big, but it hasn't had a couple billion years to form yet. So what's going on there? Actually, we don't know. It's a big open question. Another open question, uh, we alluded that we have this dark matter talk in the works. Um, and you may have heard of dark matter itself. But effectively, the observation that we can explain are several. One is that, okay, the galaxies are big. We get that. But we can estimate their mass because in some cases we know their distance and we can see their brightness and we know how bright the sun is and we can estimate that. And so we can tell, these galaxies have a certain mass relative to our sun. And based on that mass, gravity operates as a function of mass. And so we should be able to tell, what the effects of gravity are that galaxy exerts and that the stars within that galaxy feel. And it turns out when scientists do those numbers, they don't really add up. Spiral galaxies appear to rotate much faster and maintain their shape than the amount of mass and gravitational force should allow for, from at least what we can see. And that filament structure that we observe through the distribution of galaxies in the universe, um, there's not enough gravity accounted for in what we can see to maintain that structure. There has to be so much more mass for gravity to have that effect in that way. And so because of that, we say, well, something's out there. We don't know what it is, but it has gravity, and we call it dark matter. Maybe a better term for it might be dark gravity, if that's the effect that we're observing, is it this gravitational force. And it's whoever figures out what dark matter is probably going to get a Nobel Prize or something because that is one of the biggest mysteries in the universe. So there's a lot we don't there are still really interesting things to figure out about galaxies, about the universe, about how these things form. What is dark matter? How can a galaxy form so quickly when it normally we think it would take so much more time? Uh, we learned what galaxies are themselves. So if the short version of that story is galaxies are these systems of stars and gas bound together by gravity. Uh, Maybe you were waiting an hour and 15 minutes for the definition of a galaxy, and here it is. Uh, that's the technical definition, but we saw the steps needed to figure out that these are different things than the other stars and nebulae that we see in the night sky. Galaxies come in all shapes and sizes, and now you have the basic understanding of how to classify galaxies, and you can go off and contribute to science if you like. And we still don't know everything about galaxies. Galaxies are just kind of the beginning. And then this diagram on the right is a diagram of the Milky Way galaxy, and I thought it was really fun because it doesn't really look like any other drawings or visualizations of the Milky Way that I've seen. Um, but it shows a neat little um, quality, which is, excuse me, we're up here on Earth in this Orion spur of the Milky Way, and we're looking out into the galaxy from Earth in all these different directions. And these names are names of constellations, and we see stuff, right? We can see, yeah, we see these things in Sagittarius, we see these things in Cygnus. We can look towards the center of our galactic core, the teapot, if you remember from Wolf's demonstration earlier. But we can't see, not really anyways, see through the galactic core. So there's a bunch of stuff back here that we can't see, but we can infer. That's what the dashed lines are, because we can see around it. We can say, oh, you continue this shape, then, that stuff is probably there. And this is what we observe of our Milky Way. Because remember, we're inside of the Milky Way. We can't travel millions of light years away and then look back down on the Milky Way galaxy to see what its shape actually is. We have to infer it from what we see. And so this is one uh, drawing of how that's inferred. And to wrap things up, you take that drawing and you get an artist and some scientists together, and you get this, our Milky Way. So we've gone all the way around the galaxies. We've touched them all, and we're back home in our Milky Way um, to wrap up the presentation. So thank you so much for your attention and your time. I hope that made a little bit of sense. And if not, we'll record it. You can and post it. You can come back to it. And yeah, thank you so much. Any
Yeah.
questions or anything come up?
We didn't get any questions during the presentation, so everybody was riveted. That's good. But yeah, now's a chance to throw an additional question or two at Carl. We've gotten various thumbs up floating up, so thank you for those. Appreciate the reactions.
Oh, excellent.
Yeah.
Yeah, and we covered went through a lot of different things, but hopefully just give you a flavor of all the different topics surrounding galaxies and some pretty pictures, a little bit of math. Sorry about that, and some history.
Yeah.
Uh,
And then
some
incidentally,
tools.
like Carl was saying, is that there's you could probably take any little piece of this presentation and drill down for like another hour or something like that, right? And so here we're trying to give a flavor of things, introduction. One of the cool programs that SJ offers is the guest speaker series, right? Where we have visiting speakers from universities or whatever, right? And they'll talk about, their specific area of research often. And that could give you like, that extra hour on one of these specific topics. So look for that. There's also public programs you can just attend free of charge. So cool stuff. So yeah, look for that, and look for our oh, that reminds me, right? Actually, I should post our let me post one link. It's a handout that we give out during in-person sessions, and it just has some additional resources, a little bit on SGA activities, but also just some external resources that might be useful for you if you want to pursue stuff further. So give me 1 second, and I will find where I put that, and I will pop a link in the chat. Okay, here's that handout, so you can look at that if you like. And I think Carl did it earlier, but I can do it again. I can just put a link to the SJA homepage in the chat, and so you can look around. And in addition to the public programs we offer, like the Astro 101 here and various star parties, we also have various member benefits if you decide to join SJA, beyond what you see on Meetup. So we'd be happy to have you. Let's see, did any questions pop up?
There was one question,
Oh, okay, great.
and
Yep. Ah, yeah, I see
I,
it. Great.
I
Go ahead.
probably don't, I might not have the answer to this, but when we send, so
Mm.
Krishna asked, when we send radio waves towards an object, how do we know it's hitting the intended object and not any other object? That's a good question. I'm not really sure how to answer that, honestly. What do you think, Wolf?
Yeah, that is a good question. I mean, maybe so I'm making up the answer here. I don't know the answer, right? But part of it may be based on the size signature, for example, right? I mean, so I mean, we use radar, of course, to observe. Again, I'm not an expert here either, right? But planes, right? So we have, of course, radar at airports, right, or military radar, right, to survey what's going on around. And I think in many cases they can, they may detect that there's something there, but they can then detect what it might be based on the signature, meaning like the shape they see, right? Because radar does give
Mm,
some vague indication of size and shape and other characteristics, beyond just distance. So that may be one technique we use to, um, you know, figure out whether we're looking at the right thing, right? So yeah, does the thing
yeah.
that's echoing back have the expected, size and shape and other characteristics, perhaps? Again, I made up that answer. I don't know the real answer, but that sounded good,
Yeah,
right?
that sounded pretty good. I think also, I mean, it's maybe more generally, how do we know what we're observing anytime is what we think we're observing? And I
Mhm.
think the most powerful way is by observing it in different ways
Yes.
and correlating those observations together. So if we bounce radar off the moon, like Wolf said, we know it's a certain size and a certain shape and in a certain location. So if we're pointing our radio way, away from the moon and they're hitting something, it's not the moon because we know the moon's over there because we can see it with our
Mhm.
eyes.
Mhm.
So the other techniques and that cosmic distance ladder too, as we kind of went through, um, to get to the determination that galaxy really far away, we needed the Cepheid variables, and to get to that, we needed the parallax, and then these things all kind of corroborate the same story of distance.
Yeah.
Um,
Yeah, that's a really good point, right? So rarely, or maybe almost never, right? We rely on a single line of evidence, right? When scientists say, "Oh, this thing is blah light years away," right? It's usually not just a single measurement, right? It will tend to be a measurement using or multiple measurements using different techniques, right? And then we see how those different techniques agree or overlap. Same thing when you ask, how old is the Earth, right? There's not just a single measurement that gives us that number, but it's different lines of evidence, looking at different ways to try to figure out the age and then seeing, yeah, they actually kind of agree, right? And that's how we end up with, the Earth being about, 4.5 billion years old, that kind of a thing. So, yep.
for
I think
sure.
I think there was another question. Oh, any mention of our galaxy colliding with Andromeda?
Oh, I was going to mention that. I had it in my notes, but I skipped over it because I
Yeah,
was
so now people
babbling.
can't prepare. Come on, you gotta tell them what to do.
Yeah, so I heard this factoid, and and I looked it up for this presentation too. I guess the odds of this happening have gone down. It's less of a certainty and more of like a 50-50 chance right now. But yeah, that is, I think, like 10 billion years out is the best estimate. And as you saw in the simulations, when galaxies collide, they don't just like hit each other and then bounce off and everything's kaput, right? They do this kind of dance, this gravitational dance where things get plucked away from one galaxy or the stars individually get flung off and then they can actually merge completely or just have a glancing blow and then maybe come back and forth and over the eons. Um, so yeah, that's I guess a 50% chance is what I understand of that happening with us and Andromeda, but none of us will be around to see it, so we don't really need to worry about it. Maybe
Yeah.
in maybe in 10 or 20 billion years, some alien will be giving an Astro 101 talk and be able to tell us how that played out.
Yeah. Yeah, actually, that's a good point. So I mentioned it in a different intro presentation that I have, right? And I need to update that and see because in there I mentioned, yeah, it's about 4 to 5 billion years for the collision,
Oh,
but
okay.
I don't have that so you'll be talking about some revised numbers and also the probability. So that's interesting. I'll check that up. I'll check up on that as well. But maybe one point to mention is even if let's say there will be this collision, right? Collision we think of like a car crash, right? It's like right, then you've got two smashed cars at the end. But a galaxy collision or two galaxies colliding is not really like that. There's still mostly empty space, right? Even though there are hundreds of billions or a trillion stars in these galaxies, they're also really big, and for the most part, they're actually empty. And so when they collide, right, most of you will have, let's say our sun, right? Our solar system will not be crashing into anything, most likely. It'll be, flying past something. Now there'll be gravitational interaction. That's how you get some of those smudged galaxies, right, that Carl was mentioning. So there'll be a lot of interaction, but probably very few real crashes. But the galaxies, that are interacting will be, uh, forever changed, right? They'll be forever changed in their shape and structure, through this interaction. So interesting to think about, things are at huge scales, the kind we don't usually think about in our everyday lives.
Indeed. Yeah.
Yeah. Yeah, well, there was a question
Great.
about our sun will die before that happens. Yeah, if the number I remember, that 4 to 5 billion years, or what I have in my material, yeah, it's around the same time frame, right? Our sun has maybe 4 to 5 billion years to go. If the updated number from Carl is what we should be using,
Yeah, this is kind of
then
off the
yeah,
top
our
of my
sun will
head, so
expire
I might
before
be
that,
wrong.
right? And then
Yeah.
either way, we got some time, so nobody should worry. But
Yeah.
yeah, there are big events in the distant, distant future.
And like, of course, if you, again, we're representing San Jose Astronomical Association. So if you like what we're doing, check out our website. We have a full calendar of events. You can join us as a member, or you can just participate in the public ones for free.
Yeah.
You can map the Milky Way arms from your backyard using radio astronomy. Oh, yeah. I would love to get into radio astronomy. It seems a little intimidating. I'll give it a shot.
All right. Any final questions? Going once, going twice. Okay. All right. Well, thank you all for joining. I hope you enjoyed the last hour, hour and a half. We look forward to seeing you at future events, maybe here online for another Astro 101 or for one of the in-person sessions, right? So in 2 weeks, we'll have an Astro 101 in person in Hoagie Park in San Jose before the in-town star party that night. So yeah, roughly every 2 weeks, we have one of these events either online or in person. Um, Plus other star parties. We do have an astronomy beginners forum next Tuesday, actually, maybe a quick plug for that. Right, so there is a session where folks like Carl and me will be there just to answer questions primarily, right? I mean, we can talk about things, but mostly it's about addressing questions that folks might have to get into astronomy. If you're not sure how to find stuff in the sky, if you're not sure, how to go about buying a telescope or binoculars or whatever, right? That beginners forum is for that purpose. And so if you're in that space, right, check it out. Maybe join us next Tuesday. The event is on Meetup, and you can hang out with us for a little bit on Tuesday in the beginners forum if you are so inclined. Other than that, yeah, just keep an eye open for other events on Meetup or consider joining SJ for the additional member events and programs. Okay, final words, Carl, from you. I think I gave mine.
Yeah, all good.
All
Thanks
right.
so much for coming out, everyone. We appreciate the support.
Indeed. All right. Good night, everyone. And I hope to see you sometime soon. Bye.
Bye.